Okay, we'll start the class. I'm sharing the screen. So we can start today's lecture. So so this week the basic content is about wetlands. So I think you guys already know about wetland. So we'll start. So wetland water treatment uses natural and engineered systems. So there are, you can say, what a wetland. Natural wetland is there, and then artificial wetland, that means constructed wetland, that also there. So in natural wetland, that you can see, these wetlands help reduce pollution. How this will help in reduce the pollution? So wetland, as you can see, a large, there is a lot of water will be there, and there's plants, water plants and other type of plants, microorganisms, fishes, and everything will be there. And the here, that in the plants, they near the plants roots and all, and there will be a lot of microorganisms. So these microorganisms will help. So there will be water and there will be plants, and then there are different type of, this is an ecosystem. So in natural ecosystem, that you can see, there will be different kinds of plants, and aquatic organisms will be there, and microorganisms will be there. And whatever the chemicals, that not the chemical, the pollutant will be there, that is processed by the presence of this bacteria, and then it will get degraded. Not only the bacteria, also the sunlight also help to degrade this pollutant, to also purifies the water. That's what happens in the natural wetland. So to it is, we can say that to mimic this particular process, it is said like biomimic. So we are adapting from nature, what nature is doing, that we can take for our own benefits. That's what biomimic in seeing this kind of system. So seeing this kind of system, and also adapting the particular this mechanism, we can construct wetland. And then what you can do is, you can flow the wastewater. You have construct the wetland, then you can flow the wastewater. Then by the presence of bacteria, then also we are putting the bacteria also inside, and also that hydrological retention time. So these all things we are we are managing, and we are flowing the wastewater and the microorganism. We also plant the different varieties of plants, and fishes will be there. So by fishes, it depends the kind of wastewater that we are providing. It depends whether that is suitable for the fishes or not, which kind of fishes are uh, adapt that kind of environment. So we are providing the flowing the wastewater, then this will get treated by the presence of the different elements in the ecosystem, then that purifies the wastewater. That's what constructed wetlands do, and that we have adapted from the natural wetlands, which is already there. That is called biomimicry. We are adapting from the nature. So you can read here, this constructed wetlands are engineered wetlands that are designed to mimic the natural wetlands and treat the wastewater from the communities. They are often made up of settlement tank and ponds planted with wetland plants. The plants and microorganisms in the wetland break down the pollutants and remove from the water. So that's what it is doing. Now here you can see the different. So you can read the slides number 2. The main parameter, one of the main parameter we have to look into it, is the retention time. What is the retention time? Retention time is as the time a wastewater gets at particular point in the ecosystem. So if it's going very quickly, if it's flowing very quickly, what happens, it don't get the microorganisms, also it don't get that much time to degrade. So we need a more retention time. We need that particular wastewater content, that point should be in particular point in the ecosystem for a longer time, for that the microorganisms get more time for them to process. Also they will be sunlight. So the retention time is very important parameter. Retention time is very important parameter that we have to look into it. Okay, so here you can read some of the parameters, so that we can control the retention time. So first of all, design and sizing, so it depends on the surface area. So how it affects the flow rate, like how the, here you can see larger surface area means it takes longer retention time. So these also depth, if you have more depth then it gets more retention time. Otherwise if it's shallow, means this one and this one depth, so this gets less retention time, and this particular model get more retention time. So these all parameters we have to calculate prior to design a proper wetland, constructed wetland. So you can read other parameters. What are the flow controls structures, that means different gating system we can apply, because there will be pipes and gating system we can apply. And so controlling a speed controlling system also we can apply. Also water level management, pumping systems, these all things we can apply. And flow rate regulation, vegetation management, okay, that's also very important, that which plant that we can choose. Like that depends on what kind of wastewater you are putting in. So according to that we can select the plants. And then hydraulic modeling, that you can use different simulation softwares according to your, you have decided retention time, then flow rate and all, size and all you have decided. Then according to that particular parameter that you have designed, then these all, they will be simulation software. You can put this input variables that you have assumed, or you may have some small experimental data values. So according to that you will get the simulation data, and from the simulation data, that how much the treatment is gone, or how much also you can calculate that how much purity it can get. Also these all things you can model. So first of all, design parameters in the constructed wetland is very important parameters. Now you can see here, this is a wetland. So here you can see the water, salt, fresh, and somewhere between seasonally or permanent. This is a natural wetland. So you can see that in this wetland, it's not only have the water, the wastewater, it can also have salt also. So when you select plants, that plant should sustain the salt content, not only salt. Salt means not only NaCl, different kinds of salt will be there. So these all parameters you have to look which plant can grow on that particular condition. So you may heard of estuaries. So in estuaries, that most probably it is near the sea. There will be a lake, then there will be sea, and then there will be a lake. So sea and lake, there should be a barrier to separate. When some condition I think comes, so this can, we can break, and these all will reunite also. Then in this lake you can see a lot of estuaries, and you can see wetlands also in some part of the place. So these wetlands you can see, even though the salt can come into the water, it can some you can see the plants inside it can grow. It doesn't have any damage due to the salt sea water. Also the fishes inside the lake, or some of the fishes also, that it can adapt, it don't have that much problem of salt. But that also depends on how much concentration also a factor. Okay, so this is the natural wetland, that you can see there will be water content, and there's plants, and there will be microorganisms inside, fishes inside. So this is the wetland. And here you can see what is wetland. Here you can see Um, See here, wetlands are interface between terrestrial and aquatic ecosystem. In that area, you can see it is you see plants also, and also water also. There is a interface between terrestrial and aquatic ecosystem that you can understand from the figure. And then also you can see a proper definition I have given here. Wetlands are areas where a table is at near or just above the surface, and the soils and water saturated for a sufficient length of time such that excess water and resulting low soil oxygen levels are principal determinants of vegetation and soil development. Wetlands will have a relative abundance of obligate hydrophytes in the vegetation community and soils featuring hydric characteristics. So you can see into this, and then uses of wetlands also this you can read. And now the first question: which of the following is the major treatment process occurring in the wetland? That means you are constructing or in the natural also you can see what is the major treatment process. So four options are given: adsorption, bioaccumulation, phytoremediation, on all of the above. What will be? Anyone have answer? Yes, all of the above is the answer. Yes. So why you can see here what is adsorption? Adsorption you can see a process by which molecules adhere to the surface. So how this will eliminate the pollutants? You can see here physical and chemical attraction between the contaminants and the solid surface. So you can see the ecosystem of wetland. So in ecosystem, you can see there will be soil or some bed will be there, and in which the plants will adhere and grow, and then microorganisms are there. So this is soil bed or something, which can where it can adhere and go. Then water will be there. Then fishes or something like that. Then also floating plants, algae. So different kinds of plants will be there. So adsorption, you can see the process by which molecules adhere to the surface and it can eliminate. So bioaccumulation, you can see when the microorganism, the accumulation of substance in living organisms over time. That means the pollutants which is present in the water, it can it is processed by the microorganisms which is present in the water. Then what happens? It is degraded, and that can be settle down in the bed. Like that the water become clear. And also one more process, that is photoremediation. Photoremediation, how it comes? Sunlight. So sunlight, and then the sunlight will come into the water, and then it will the different pollutants will be there. Due to the presence of this light, the pollutants will degrade. Like that the purification is happening. So these three things are happening in the wetland ecosystem. That means even in the constructed or in the natural ecosystem. So second, the correct arrangements of units in conventional aerobic sewage plant. So one, two, three, four, five steps are given: screening, primary sedimentation, aeration, grit removal, secondary sedimentation. So what will be the initial from starting to which one? Which one? Yes, option C is the right answer. Yes. First is the screening, then grit removal, primary sedimentation, aeration tank, and secondary sedimentation. So you can, yes. Then third question, the role of vegetation in wetlands. So four options are given to make it look attractive, to grow the food crops for consumption, or to remove the contaminants through bioabsorption or and bioaccumulation. And the none of the above. This is very easy. Yes, C is the right answer. Yes. So C is the right answer. Okay, I will show you one video also here. So you can see here. So you can see here. See, this is now you can see how the constructed wetlands, how they are doing. See that they are taking out, they are digging a portion where, according to these digging, the size, na, the size and all, you should have a proper, calculation. And then water, the wastewater, you can see here this point. I hope you can see. This is water, that inflow water you can see like that. And then you can see the plants which is grown in the ecosystem wetlands. And then this is the wastewater, and they will be microorganisms. So this get treated as the time proceeds. Okay. The sea, you can see the inlet pipe. So okay, see this inlet pipe, how you can clearly see the from the video. Is it clear? So yes, see here also, this is natural wetland, so that also you can see. So this is the natural wetlands, that you can see the roots also, the plant's roots and how it is. Okay, so I hope that this is clear. Yes. Okay, now, so this is also wetland pictures now. So what is the correct order of phases in SBR operation cycle? Sequential batch reactor cycle. So what is the correct order of phases in SBR operation cycle? So what will, so four options are given. So which one is the order? Any idea? Okay. Option B is the right answer. Fill, react, settle, decant, idle. I will explain. So first, this is the sequential batch reactor operational cycle. So how it has, how many cycles it is given, like five cycles it is given. So first is fill phase. So fill phase means wastewater is introduced into the reactor. So this is, we are talking about SBR. So first phase is fill phase. First phase is fill phase. Fill means we are first filling the wastewater into the reactor. So uh, this is like we should fill also as per the design calculation, predetermined volume of the water that we have, that already we calculated, that we are filling in the first stage. That is the fill phase. Fill phase. Then what is next phase is the react phase. So in react phase, you can see aeration occurs, allowing microorganisms to degrade organic matter in the presence of oxygen. That will be helped by the aeration that we are providing, so that the oxygen presence will be there, and the microorganisms which is present in the wastewater can degrade the organic matter in the wastewater. So this react phase, it is given, it can vary depending on the treatment requirement. So if the wastewater is too much, the loading, that means very high, that means the wastewater, the concentration is very high, then we require more time because it has more organic matter in the wastewater, so we need more time to process this. That means the react phase is longer. Okay, that I hope you understood. The second phase is react phase. So in the react phase, see, there is a wastewater which is less concentrated. This is W1 and this is W2. And the concentration, this has W2 has higher means concentrated than W1. So that means this particular one, which is very much concentrated, need more time to process the organic matter which is present in the water by the microorganisms to degrade it. Okay, so this is the biological treatment that happens in the react phase. React means something is reacting. Okay, then the third phase, which is settle phase. Fill phase, filling. React means reacting. Then settle phase. Settle phase means aeration is stopped and allowing the mixed liquor to settle. So the degraded thing, the it will settle down. Now the aeration is stopped. So next is the settling phase. Settle phase. Then what? Fourth is the decant phase. Decant means the clarified effluent is removed from the top of the reactor, and the also to discharge treated water while retaining the settled sludge for the next cycle. So now also effluent, to clarify, the effluent is removed from the top of the reactor, also to discharge treated water while retaining the settled sludge we just retain for the next cycle. Then fifth one is idle phase. That is, the reactor may remain idle. Next is the decant phase, removing decant. Then last step is idle. Idle means the reactor may remain idle for short period to allow any remain solids to settle further. This will improve the effluent quality before the next fill phase begin. Okay, these are the different steps in the sequential batch reactor. Fill phase, filling the wastewater. React phase, the organic matter which is present in the wastewater will react, means it is degraded by the microorganisms. Then the sludge will settle, and then decant, we are removing the effluent, and also the remaining sludge will settle. That is, for the next cycle it is retained, and the idle will just operate the system little more time, so that the remaining solids, if there, then it get more time to settle down. So this will improve the next before going to the next cycle. This particular idle process will again clear the water which is remaining, so that next cycle will be not much more concentrated. Okay. 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 Any doubt? Yes. Yes. No, no. Here the effluent we removed. Then what happens? The reactor may some liquid will be remained. So what happens if it is more concentrated? Again, when we add more liquid, the whole liquid will be much more concentrated, because this particular will be more concentrated. Then what happens? We give more time so that the remaining solid which is there present in this liquid to settle, so that this particular liquid will be somewhat clear, so that when next cycle will come, the whole system is under the limit of treatment. Got it? Got it na? Okay. Now, next one, the components responsible for removal of contaminants in the wetland include. So, options are lining and vegetation, B, vegetation and substrate media, C, inlet and outlet arrangement, D, all of the above. What are the components responsible for removal of contaminants? Any idea? The answer is B, vegetation and substrate media. So how this come? What is substrate media? Any idea? What is vegetation? We know, we whatever we are planting these vegetation we know. What is the substrate media means in wetland? No. Substrate mean substrate. Okay, you see. So mainly the substrate means, see, vegetation we have in the ecosystem. Other than that, you know the bed here. This bed, which will be like a home for the microorganisms, or it the for the plants, it will attach and grow. That means, for example, it's a soil. This is called the substrate. It's a bottom part of the ecosystem, bottom part of the wetland ecosystem, which is constructed, or the natural, which is on the bottom solid media. That is called the substrate. Okay. Any doubt? Okay. So you can read the. Huh. Yes. Yes, here also the microbes in the constructed wetland, we are providing even debris or soil or whatever that we are providing as a bed. That is called the substrate, soil or debris or whatever we are providing in the bottom of the ecosystem. That is called the substrate. That can be biotic or abiotic also. Yes, what you said is right. Like that, in that it we provide in the system, inside the system. Here we are, what we are paving in the bottom of the, in a, we are digging something in the soil also. What we apply in the bottom, that can be biotic or abiotic. That can be the home of microorganism. All, if the soil particles are there, the that plants also, it will attach here and grow. And some of the plants which don't need the attachment, that will be floating in the water. And microorganisms, like it will be, in the roots, near the roots, or inside the soil, it can be there, or also in the water. Okay. Next, you can read this substrate. So here I have given what substrates can be biotic or abiotic. The Here you can see substrate provide a secure place for animals and plants to attach, shelter, and find food. So that's the substrate. Then substrates are foundation for ecosystem, and they regulate interaction between the groundwater and the surface water. That you got right. So here, as I said, this is the bed. That bed that we are giving us the substrate, and above this bed, this is substrate, and then substrate, and above it you can see the water, other plants, fishes, microorganisms, and inside also microorganisms are there. And below it there will be soil, and then you can see the groundwater also. Then in some time this groundwater also can come into the whole system. That you can see, about the capillarity, capillary mechanism. So in the soil also there will be pores. So when this pore size are, that means the critical radius of the, if it's under the limit of the capillary action to take place from the groundwater, the pure water can also penetrate into the system. That also can happen. So here the substrate is the linking factor between the above wastewater and the below pure water. Okay, then also substrate can filter the water and reduce. Okay, these all things you can read. So I hope now it's clear. Yes. Okay, then next question. In a typical SBR, the aeration and mixing is avoided in which stage? First stage, second stage, third stage, all the above. So in SPR, we have just discussed. So in which stage we have to avoid aeration and mixing? Yes, third stage. What is the stage? What it is the process you remember? Sorry. Yes, settling. Right, right, right. Settling. So settling, we don't need to, we are just putting the system as it is. We are not disturbing the system so that the proper settling can happen. So if you are mixing it, what happens? The turbulence come. Then the flow will be in a different way. So that the settling will be, it is hampered because of the, the flow. So the settling, we are avoiding the aeration and mixing. So this you can see. So settling this phase. So this reactor remains undisturbed, allowing the solids to settle naturally to the bottom. Now, seventh question. Match the following process with stages in MBR. So, um, different two columns are given. We have to just match it. So, from this, any answer? First itself, you, yes, C is the answer. Yes, C is the answer. So here, from solid liquid separation, as we know, solid to liquid separation membrane is needed. And then oxygen supply, that is easy, that aeration. And then BOD reduction, microorganisms. So like that, C is the right answer. Next, biomass growth in a sequencing batch biofilm reactor. Sequencing batch reactor is predominantly fixed bed attached growth, suspended growth in water, attached growth on suspended carriers, all of the above. So, what will be the growth mechanism? Which one? So, answer is attached. Ah, yes, attached growth on suspended carriers. This is the answer, right? So, here I have given also, so you can read sequencing batch biofilm reactor. So, as you can see, what in sequencing biofilm, here it is come SBR was first. We have answered few of the question related to SBR. So here come SBBR. What will be the difference? So here biofilm is also added. You know how it is different? Yes, just suspend. Yes, in SBR this is just a suspended. So here you can see, um, SBBR, sequencing batch biofilm reactors, are advanced type of wastewater treatment system that combine the principle of both this thing and biofilm technology. This approach effectively enhances the treatment of wastewater by utilizing biofilm for degradation of organic matter and nutrients. This biomass is attached to the biofilm. So that you can see here, microorganisms attached to the support media. So in the biofilm, example, here you can see plastic media or stones within the reactor forming a biofilm that aids the biofilm means onto the plastic or stones, the this back microorganisms will attach. Then what happens, it will form a biofilm by multiplying. They eat something and they film a biofilm, multiplying and form a film. So this film will help in the process of wastewater treatment. And then I have given the difference between what is the attached growth. So here, this is the suspended growth and this is the attached growth. How can we differentiate the suspended growth and attached growth? Yes, attached to here it is stone, then example they just told stone, then it is attached uh, to the stone and it is growing. Here it is just suspending, and we are providing food also here just in the suspending manner. Okay, now compared to conventional ASP system. Yes. Yes. Sorry. Yes, yes. Sequential SBR, right? Yes. Yes, in SBR, it is in the suspended sequential bio. Yes, I asper. Okay, let me. Okay, I will tell you after the break. If I'm thinking yes, it is. Yes. Huh. Yes, and growth is attachment is there, and food we are providing also in the from food it is getting. Yes. 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 Suspended form. That's what as per I'm thinking. Sorry. Completely packed fixed, or it is just floating in the. Yes, yes, that you have to. So I think both type of systems can be available, fixed and floating also. I will just tell you some examples like after the second half. So if some correction is, I hope that they will be floating also. This even the stone, it is the weight is heavy, so that it will be not float that much. But uh, if you provide plastic is there, then if it's not fixed, it can move also. I will discuss after the break if any doubt like changes there. Yes. Yes. So in here, compared to conventional activated sludge process systems, a membrane bioreactor operates at. So four options are given: higher sludge concentration and lower reactor volume. So you can read what will be the activated sludge compared to the conventional activated sludge process. What is the MBR when we compare membrane bioreactor works at the on the basis of the sludge concentration, what will be the correct, which one will be operating in higher sludge concentration. So here answer is A. Higher sludge concentration is here the answer here. Membrane bioreactor MBR. It works at very high. It is works at higher sludge concentration and lower reactor volume. Reactor volume means the amount of water that we can process is less compared to the activated sludge process, but we can treat higher sludge concentrated wastewater. And also I have given here conventional ASB and membrane bioreactor. First process type, conventional activated sludge process, biological treatments with suspended solids. So suspended solids are there, like that we are treating. But in membrane bioreactor, there is membrane is there, and we are integrating the membrane with the membrane reactor for the it here for the filtration. So you can see separation method: secondary clarifier for solid liquid separation, here membrane filtration. Okay. um, it's a photo type. I Okay, this way I can just few things that we are, I hope yes. Okay, so here you can see microbial retention time. Microbial retention time, how much time they are getting for the processing of organic matter. So in ASP, it relies on settling of activated sludge. And but here in membrane bioreactor, microorganisms are retained by the membrane. So here the membranes, microorganisms are retained by the membrane. So here it is not depending on the settling of any sludge. So here it is getting more time to process. And effluent quality and footprint. And also there is one more thing that I have to discuss on. It's energy consumption. Energy consumption. So okay, cost is coming. Okay, then at least cost we can discuss. So here cost, generally activated sludge process need lower cost, and operation cost is also less. And then, but here when we see the MBR process, it is the capital cost is high due to the membrane technology. But also it can say also here the post treatment we can save in MBR if you are using MBR. So when we comes about the cost, activated sludge is not that much costly, but MBR is costly because membrane parameters that we have to fabricate, and then we have to optimize the membrane. So even optimizing the membrane is a very, it's a critical parameter, how much thickness we need for the membrane reactor to work. And also that thickness will vary according to the concentration of wastewater that you are processing. That is also important. Okay, so now next question, which is the following is true regarding the different configuration of MBR? So here you can see about, they are discussing about side stream and submerged. So about the energy consumption. So here option A is low energy consumption is the advantage of side stream configuration. Less rigorous cleaning procedures needed in submerged configuration. C, submerged configuration typically have higher energy consumption. D, all the above, which is the true statement regarding the MBR. Any answer? So the answer here is B. So less rigorous cleaning procedures are needed in the submerged configuration, which is this one. So you can see here when we compare side stream and submerged configuration of the MBR. So here you see here the membrane is fully merged inside the reactor. So here it is separated. But also you can see why it is here it is for the sides stream, it is not at like flexible. Why it is flexible? And here it is less flexible. So that is mainly because here in the side stream membrane is in the separate compartment, I mean separated. So in submerge it is inside. So the cleaning and all will be, so when we see that here less rigorous cleaning procedure required for the submerged configuration, but every time we have to take it out and then clean. But here when we look into this particular thing, we can easily, whatever happen, we can easily displace thing. That's why flexible meaning. But here the less rigorous cleaning is needed for the submerged one. Here it need more cleaning, but for the when we analyze the flexibility also, we can have the flow rate or something, the different parameters also. This we can manage more flexibly, we can control. That's what here flexible. Then flux, when we compare the flux side stream have higher flux. Then energy consumption also, side stream has higher energy consumption, and submerged has lower energy consumption. And here when we analyze the membrane packing density, the density of membrane is less. Here for the submerged one, higher membrane density is needed. Now, so okay, this you can read out. Next question. Sorry. Yes. So here in submerged you can see the flow velocity and all will be different than the side stream. Here it is applying more, um, it is we are applying from the one side. We have to apply, we are flowing the liquid into one side of the membrane. Like we are putting this the solution here, and then membrane is situated here. But here you can see it is submerged. In the submerged you have um, you know the the flow rate which is here is comparatively less compared to the size stream. Here we are fully, what exactly it say, um, okay, how should I explain? So see, here you it is mentioned high membrane packing density is needed for the submerged. So the membrane density is high. Density is high means it is highly packed. Highly packed means its pores and all are tightly packed. The pore size and all also less. Pore size is less. So here it means densely packed means for the fouling or the which is clogged inside will be less. But here it is low packing density. So here we are providing the low packing density, which is thin membrane, thin also density is less. So that means here the pore size is, it is higher. And also the foul and the different organic matter can clog in the system, so it needs more cleaning. Here it is tightly packed. It is due to the morphology, and mainly due to the morphology of the membrane. Clear? Okay, still doubted. Okay, uh, I will clarify this. I will show something. Okay, yeah, I will clarify this thing. Then, and also here it is not the cleaning of the membrane. So here you can see it is on the whole system it is saying, right? Okay, less rigorous cleaning. So I have given here easier to clean. So here in the submerged configuration, it is the integrated design. Membranes are submerged into the mixed liquor, allowing the simpler access during the cleaning. So lower energy cleaning can be often done with lower energy requirement. Continuous operation. Be cleaned while system is, yes. So you have heard about backwashing. Yes. So in the submerged, so you they are saying even when the system is working, also the backwashing is also possible. So that the we are using DI water or some pure water to clean the membrane in the system without stopping the process. So that is easier in the submerged configuration. But in here, as I told you, the fouling rate is higher in the side stream. I hope that mainly because In the side stream, it is less dense packed membrane, but in the submerged configuration, we need thicker, tight membrane. So that is uh, due to this densely packed membrane, the pores also, and there is other parameters comes for the fouling, that is hydrophilicity and hydrophobicity, and also texture also comes here. So the texture, depending on this, fouling can happen. So fouling, okay, I will clear this thing out, that um, why this fouling happening in the submerged more. Okay, then the selection of choices for wastewater treatment system depends on regulatory requirements, installation and O&M cost, operating and maintenance cost, intended reuse or disposal, all of the above. What will be the answer? Yes, all of the above. So when we go for a wastewater treatment, so first of all, we should know the design and all. We have to analyze. For the design also, we should know what type of wastewater we have going to means process, that different type of wastewater. We have the home wastewater, that means from the if, from home means different type of wastewater is generated, that we already discussed, and also from the if it's from the hospital, it is different, and it is desalination means it is different, and then oil and wastewater industry, it is different. So according to the wastewater type, we have to choose the wastewater system. And then a regulatory requirements, why it is needed. So whatever the wastewater it is generated, the regulatory requirements according to the government, there will be some permitted limit of the TDS or the concentration, so that is safe disposal of the water in soil or water sources, or soil or water. So that particular limit, so there will be some values. So that particular limit, we if we cross, then we can't dispose the wastewater. So then we have to again treat that wastewater, and then make the wastewater under the limit of safe disposal, and we can dispose. That is regulatory requirement. Also, if you want for the consumption, then also regulatory requirement, that there will be permitted level of elements in the water. So these all things comes under the regulatory requirement, safe disposal, or for the further usage also, how much chemical composition and level of chemicals can be accepted. Then installation and operation and maintenance cost. Installation will be there. Installation, we have the proper area there, we install, and then we need electricity, we need pump facilities and all. So these all installation cost, the that we purchase initially, comes for the installation. Then operational cost comes, every day we need electricity. Then maintenance means, if the membrane here, if in the wastewater itself some leakage or something happens, or daily cleaning of the system is needed, or if membrane is using, you have a particular limit for the membrane that can be used. After that particular time, the membrane will not be useful for that step, that we have to replace. Or by the time we can use it by backwashing, we can clean the membrane and reuse. But at a particular time, your membrane is terribly fouled and you can't use it, so that time you have replacement cost. Then reuse and disposal. So how much that we can reuse means, like reuse for your agriculture or different other plant, that plant in the sense some factories you can use. Then disposal of wastewater, these all comes in the wastewater treatment system cost. Next is the biofilm carriers in the MBBR should be capable of disinfecting microbes, inert inert, that means non-reactive, or specific gravity significantly higher than water, and having very smooth surface. So what will be the biofilm, that property of mbbr? Any answer? Yes, right, B is the answer, inert and non-reactive. So why it is? So I have given just given the property of a proper mbb BR biofilm that we are using, what will be the properties needed. So first of all, material composition typically made from inert materials like plastic, ceramics, metal, or ensuring durability and resistance to corrosion. That resistance to corrosion means if you use a metal, normal metal, then what happens? Corrosion happens because there are different varieties of salt present in the wastewater. So plastic is inactive, ceramic, metal, but this metal comes if it's not reactive to that particular type of wastewater, and also concentrated way, which type and how much concentration it has. Then that copper, iron, these all things easily corrode, right? Then silver, you can think silver, but silver and cost is high. Then surface area, so high surface area to oleum ratio is not needed, by because it is it if it has very large surface area, it will allow the microorganisms to attach and grow. Okay, so so for example, see so you I don't know whether you guys have heard of lig means it's a laser induced graphing. Okay, so what we are in our uh, lab, what we are more interested in ligs. So graphene, that how graphene is synthesized by different varieties of different kinds of chemical processes are there to produce highly pure this graphene. But here what we are doing is we are producing laser induced graphene on a carbon substrate, any carbon substrate we are taking, and we are producing laser induced graphene. The main the advantages here, this laser induced graphene, it has different different structures. That means it's a fiber structures it has because of the burning of the surface. And this surface, if it has the fiber like brush type surface, it has more surface area. So you can see that the microorganisms can grow, attach here and grow. See, if the surface is here, it has more surface area. If, for example, here the surface has more brush type surface, then what happens? This microorganisms can attach here in different areas, then it can grow. Compared to the very plain surface, here you can see that the home for them is higher. It has higher surface area. Attachment is easy, so that it can grow efficiently. Then porosity, we may have porous substrate to enhance the water flow and facilitate nutrient exchange. Then buoyancy design remains suspended in the that you can refer. Then surface texture, so even for some of the application, surface, we can texture of the surfaces, we can texture the surface according to our need. That you can read how to texture the surface by different methods. So other you can read. And also this thing, mechanical strength, so the mechanical strength of biofilm should be good so that it can withstand the hydraulic forces also. And also chemical resistance, and that's also important point. Now, here, which of these following would be better suited as carriers that provide surface for biofilm growth in mbbr? So four options are given. high density polyethylene, then melam. No, it is not C. A is the answer. So it is a polymer. It is a polymer only. It is here. It is why it is high density is there, and I have to refer. I have to understand like why it is you know it is suitable for compared to other materials. Why it is providing more biofilm growth. Any idea? So different properties of this is there. It is strong, durable. Okay. Yes. Okay. That's all. But there is other parameters like durability and yeah, it is lightweight, but chemically resistance. These all things. I hope it will come chemically resistant. This is strong, durable, and then also it is. You hope, and also as you said, it is lightweight. But I have doubt with this polypropylene, this one also, because it is density is 8.87. Huh, yeah, but I have doubt the answer they have given is this one. Yeah, even I have doubt that they haven't chose this one in place of this, because compared to all this density values, this is the lowest density. But okay, I will refer. Maybe it is due to some, maybe the casting cast. Yes, also yes, and also the casting, like how easily it can be fabricated, fabrication. I will clear this. The answer in the booklet is this one. I will refer other things, especially this one, polypropylene, and discuss this one. Yes. Okay. Then, yeah, the properties of this HTP, it's here that you can read. The good benefits of the usage of this HTPE. So it is chemically resistant. HTPE resistant to wide range of chemicals, making it suitable various wastewater treatment. And also it is durability. Mechanical strength is good and durability. Then it is lightweight and easy to handle. And then low density ensure buoyancy. Then high surface area, then non-toxicity, and then thermal stability and cost effectiveness, easy to clean. The smooth surface of HTPE allows easier cleaning and maintenance, reduce the fouling and extended life of the carriers. So this is the HTPE benefits. Now this one here, match the following. So SBBR, MBR, MBBR. So it is for wastewater treatment things are given, and then we have to match. Any idea? So SBR configuration of ASP in which processes are operated in batches in the same reactor. Then SBBR, so here SBBR biofilm is added. So It means B D, right? Yes, biofilm. Then MBR, yes, A. Activated sludge process plus membrane filtration equipment. Then MBBR, then remaining is B. Conventional biological treatment plus attached growth of biofilter processes. So the answer is C two. This A. A is the answer. Now that, yes, I have given the this, you can read difference between this process, that SBR batch biological treatment, here SBBR batch biological treatment with biofilm. This is a membrane bioreactor, and here membrane bioreactor with biofilm also comes here. So the different things you can read out, difference between these four reactors. Then difference between a biofilm and membrane is given, that also you can refer. So biofilm and membrane. So here in the biofilm, a layer of microorganisms that attach to a surface, that is called the biofilm. Membrane is a barrier that selectively allows certain substance to pass while retaining the others. That you understand, like bio means biofilm means bio, because bio means microorganism that creating a film, that is called biofilm. Membrane is another thing that we are fabricating by using different polymers. So or that we are fabricating for the specific purpose. Also we are adding pore forming agents, also if needed specific spore sizes, like that we are fabricating membrane. Then structure typically porous and layered, can grow on various supports, that is the biofilm. And then here composed of thin films made from polymers, ceramics and metals. So you can read other things. Next, the degree of fouling in MBR depends on feed and biomass properties, membrane properties, operating conditions, all of the above. Which one? Yes, all the above. Right. So why this fouling? Like in fouling means if the feed and biomass property, feed has a lot of organic content, then fouling will be com- proportional. Like it will be high. And membrane property that I have told, if there is if we are using a membrane for that, then if the membrane is if membrane has some brush type something like this, or some brush, or not membrane surface, or anything that it has some type of some hanging in some anchoring points, then this microorganisms can attach and grow. But if it doesn't have anything, or it is somewhat smooth, or it can't attach that much. So that means the texture of the surface, and also hydrophilicity and hydrophobicity of the surface. Then operational conditions, these all things will matter for the MBR fouling. Okay, so now I think we can take a 5 minutes break, then we can come to the previous class discussion, ion exchange membranes. Okay, we'll take 5 minutes break. Yes. Yes. Any doubt? We can start the lecture. So first of all, ion exchange membrane. So here, uh, ion exchange membrane, there will be two types: anion exchange membrane and cation exchange membrane. So here you can see. Just wait, I have. Yes. So here I will see this is the polymer. You can see this is a polymer, and you can see the charges. So have you guys heard of different types of polymer and that is how it is fabricating and all? Okay, so different types of membrane is there. So mainly, what polymers that we normally that we cast for RO, or different types of UF nanofiltration and all, that is different. And for the ion exchange membranes, the fabrication step is little bit different, because we should need a movable charge for the exchanging of the ions which is present in the wastewater. So here, anion exchange membrane, what is the charge of the anion exchange membrane? Cation exchange membrane is negative. So here you can see, this is the polymer chain. So this is the polymer chain, and this in the polymer backbones, this is called polymer backbone. And here there is a functional group. Here it is fixed, one is fixed, one charge is fixed. In anion or cation, anion exchange membrane or cation exchange membrane, what happens is, in the polymer backbone, one functional group is there which is in the fixed charge, that can be positive or negative depending on the anion exchange membrane or cation exchange membrane. And there will be another charge which is floating, it is movable. This red dots which is seen in the figure, it is movable, it can move. Okay, so this is the movable charge. So what happens is, one charge we are making it fixed, and another charge we are exchanging, so that this negative charge, if this is negative, then the negative from the salt solution, that is the wastewater, it is exchanged and it is moved. If it's positive, and then positively charged salt or ions are exchanged with this, and then it can be moved into the another compartment. So I will show. Okay, this is one of my colleague who has prepared a, ion exchange membrane. So I have just taken his presentation. So he is mainly working on ion exchange membrane. So he has used, as he explained, we can either use the different techniques, NIPS or TIPS method for the uh, construction, I means fabrication of the ion exchange membrane. So anybody have fabricated membrane anytime? Okay. So okay, then I will take how the fabrication of these things in the I will take one extra class. So that will, like, I think cover these things also. I will take that time. So here it is NIPS, non-solvent induced phase separation. That means, like, the membrane, which is we have some solvent and solution, polymer will be there and solvent is there. So for example, if we have so this is not ion exchange which I am talking. A polymer will be there. Yes, yeah. In ion exchange also there will be a polymer plus there will be a solvent, and then what happens is, we just cast on the on the surface. Then we just immerse into a non-solvent, so that will cause solvent non-solvent demixing and then forming the polymer layer. And here, thermally induced polymer separation, we are heating the polymer solution and making it solid. Thus the solvent will vaporize and the polymer will be solidified and we get the sheet. And here you can see he has put a here you can see different, he has explained about the anion travel. So a result of concentration difference and the potential difference. Here you can see, in an anion exchange membrane, so in the anion exchange membrane, how the charge floating or charge exchange, how it take place. So anion exchange membrane, it is positively charged, and here you can see that the positive functional group is fixed in the polymer backbone. Polymer positive charge is fixed and the negative charge is floating. Negative charge is floating, it is uh, exchangeable. So first you can see different mechanism by which the ions are moving through this ion exchange membrane. So here first is, see, this is surface side hopping mechanism where ions are just jumping from one to another point. I hope you have seen. See, yes. So next, that is called hopping mechanism. And next is growth's mechanism where the proton hop from one water molecule to another water molecule. So that is clear. So here you can see is, it will, this ions will pass through from one water molecule to another molecule, and that means hydrated anions continuously form and break the hydrogen bonds with the water molecules. That is the growth mechanism. See, ions will come and pass through the water molecules and break this hydrogen bond, and then it is moving to the different site. And then last is the vehicular diffusion where the anions move with the water, where there is a lot of water. The main way the ions will move is with the water, it will move. If there is more water, then it, what it does is, the ions also move with the water. You see the ions are moving with the water. Got it? These mechanisms are clear. Okay. Now, so that is the ion exchange membrane. So now we'll see that here you can see. So in how it is working, I yesterday in the previous class also I told in the electrodialysis, you see the anion exchange and cation exchange are different, alternately it is arranged in a chamber. Then we are providing the water we are providing, and what happens is, see, then we are applying a DC supply at two ends. When we provide this, what happens is this, if it's anion exchange membrane, that means positively charged, that is positive charge is fixed in the anion exchange membrane. That means negative ions it will just pass through, that by these three mechanism which I explained in the slide. By this three mechanism, the negatively charged ions it will pass through the ion exchange membrane, but the positive charge it will repel and it will be, it won't pass through, it won't allow to pass through. So here I hope that you can see, um, see here, this one, this particular membrane, can you comment which membrane is this, anion exchange or cation exchange? This blue color, you can just see. The blue color membrane, what is it? Is it anion exchange membrane or cation exchange membrane? Any idea? Didn't understand. See here, what you have to understand is that this is the polymer backbone. Okay, so as I told here, see, this particular graph, we have to understand what is anion exchange membrane and what is cation exchange membrane. So, first of all, in anion exchange membrane, we are taking it is the polymer backbone, and then we have a functional group, fixed functional group, and it has a charge. Okay, so in the anion exchange, this particular fixed functional group, the charge of this fixed functional group is positive. Okay, so movable one. Movable one means it can be exchanged, it can pass through. That means here, so I will take some other color. You can see this particular points. This is the ion, like this groups can be exchanged. And what is the charge? The charge is negative. This has the negative charge. So here this is if this membrane is has positively fixed charge and negative it can be exchanged, it is movable charge. Then now we you consider one thing. Oh, sorry. Okay, this is the backbone, and this backbone it has fixed charge positive, fixed charge positive. Then we have the movable charge negative. This is called anion exchange membrane. Okay. So how the exchange take place here? This is negative. Okay. So this is anion exchange membrane. So now you can assume NaCl. NaCl in a water. In a water, what happens to NaCl? It split in Na plus and NaCl minus ions will be found, right, in the water. Now assume that if the this is the membrane and we have the uh, see here we have this is the whole surface. Okay, this is a whole surface, you can assume, and we have Na plus. What do you think? Is this polymer allow NaCl to pass through it? No, right. What happens? It will repel. Since its fixed charge is positive, it will repel. It can't pass through. But when you see Cl minus, the Cl minus can exchange with this ion, this one, which is this is negative functional group, and like that it can pass, exchange, and then it will pass to another different mechanism which I explained here, by either by moving to different jumping to different functional fixed functional groups, or with the water it can move, or by hydrating also it like water also it can move. So by different mechanism the Cl minus can pass through this anion exchange membrane. Okay, any minus charge salts. Also, one more thing, it depends on if if the ion exchange polymer that we are fabricating. Also, there is one more point that we look into it: the size of the ion, size of these ions, and the also matters. Okay, I am just giving an example. This is the basic thing that I am teaching, but there is size of the ions also important parameter. Okay, so here this is happening. Here Cl minus can pass through, but the Na plus can't pass through, and here that is called anion exchange membrane. Now it comes to cation exchange membrane. So in cation exchange membrane, you can see fixed charge is negative. So fixed charge is negative. And then there will be movable charge. This yes, this movable charge is positive. Okay, this is not visible. Okay, this movable charge is negative, positive, positive. So at each functional group which is fixed, there is the movable charges also, that is positive. So now you consider NaCl here. So did Cl will pass through it? No, because it's Cl minus, so it don't pass. Na plus, assume the Na plus. The movable charge in this polymer backbone is positive. So what happens is this Na plus can be exchanged, moved, exchanged like that and pass through the ion exchange membrane. Got it? Is it clear now? Okay. So like that, when we go for here, in this step you can see where the Cl minus, this Na plus and Cl minus, where it can be passed through. When this, you can see here which negative charge, so where the negative charge can be exchanged, that is called anion exchange membrane. So here you can see in the figure where Cl minus can exchange. See here, this particular blue colored surfaces. See here, it is passing. It is passing means it is anion. Here Cl minus is passing. So in Cl minus is passing. So that means okay. The half processes electrodialysis, and electrodialysis reversal also explained in the particular video. So you can see here first electrodialysis, both are like same only, but we are just changing one membrane to another polar, a charge, so that the fouling, it's a kind of like we are the cloak thing can be open and then also continue the process. That is the electrodialysis. So here you can see Cl minus. So here Cl minus is passing through the blue colored surfaces, and here you can see in the brown colored surface, it is what you can see, blue colored surfaces is passing Na plus ions, and then you can see this here. Understood? Is it clear? This electrodialysis is clear. And one more thing that you have to understand is this concentrated and where it is constant. See here. So here where the dilute stream is forming and where the concentrated stream is forming. So in the alternate chamber, there is the cation anion exchange membrane, and cation exchange membrane is there, as you can see in the figure. And here, if the anion exchange membrane is here, you can see it is passing Cl minus. So here it is Cl minus is passing and it is reaching in this chamber. And this particular brown colored surface is cation exchange surface. So it will pass Na plus. So from this particular compartment, it will, the Na plus will come, and from here this particular compartment Cl minus will come, so it will regenerate here NaCl, and this particular compartment will become concentrated, and this particular stream become what, it become diluted, this also and this also become diluted. So here you can see this also, this blue is anode exchange membrane, it will pass Cl minus, and this here also this Na plus is passing, and this particular chamber become concentrated, this has become diluted. Sorry. Yes, I'm showing the, it is not visible. Okay. Just let me, okay, just mm, this point is not visible, right, which I am now. Okay. Uh-huh. That is not visible. Okay. Okay, okay. Like that, I will tell. There is no other. Okay. Like that, I will tell. Yes. So you can see this is the, okay. First chamber is this one. Let me something I can no. So you can see here, this is the first chamber. First chamber is from the top, I am saying. From the top, first, second, third, and fourth, fifth. And first chamber, you can see this is DC supply is supplied, and here the top portion is negative and the bottom is positive. And here you can see in the first compartment, from the first compartment, it is fixed anion exchange membrane. First one is anion exchange membrane, and then second brown colored is cation exchange membrane, and then again anion exchange membrane, cation exchange membrane. In the first chamber that you can see, so you see here in the first chamber, so in the first chamber I am seeing, so the concentrated solution is coming, and this through the blue you can see Cl minus is passing. That is clear, right? This blue color is the anion exchange membrane. This anion exchange membrane is the blue color. In this blue colored surface, in all the blue color, two surfaces are there in blue color. You can see Cl minus is passing. Cl minus is passing, and then you can see in the next chamber. See in this figure only. See in the this brown colored, you can see Na plus is passing. Brown colored surfaces Na plus is passing, and in the blue colored surfaces Cl minus is passing, and in the blue colored you can see that Na plus is rejecting, it is repelling, it is not passing the positively charged ion in the anion exchange membrane, that is here it is blue colored. So you can see in the, in you, and also when you analyze, this is first chamber, you see in the first chamber, in the first chamber also this blue color, it is passing Cl minus into the second chamber, and you can see in the third chamber, in the third chamber, here this is a brown colored surface which is cation exchange membrane, here it is passing the Na plus in the second chamber, and you can see in the second chamber, from the first chamber Na plus is Cl minus has arrived here, and in the from the third chamber Na plus is also arrived in the second chamber. Like that, NaCl is regenerated here and it is becoming concentrated. Got the point? It is clear? Oh, it, I think I have stopped. Yes, yes, this one. Yes. Then when you analyze this particular thing, see in the next one, so this is positive, you can see first it is positive and this is negative, and the whole in the first chamber, from the, in the second chamber you get concentrated, After some point, you see, here, in the first chamber it become diluted, in the second chamber it become higher concentrated, in the next chamber, in the third chamber it is diluted, and in the fourth chamber it is concentrated. Like that you can see this concentrated stream we are taking out, and the diluted stream we are, if it's fine, we can just go for what else you can do. And here you can see first in the DC supply this is negative and this is positive. Then at the next time you can see, and also you see the surfaces are clogging, you have some foulant or something is there. In the blue colored surfaces also you can see, in the first surface, see something has attached. In the next time you see that you have reversed the polarity, like the charge. Now it is positively charged and this is negatively charged, and now you can see the surfaces. Like that you are doing, you are converting, you are exchanging the anion exchange membrane to cation exchange membrane, and cation exchange membrane to anion exchange membrane. So that your surface was, if first time your surface was anion exchange membrane. See, in the first example I told you this blue surface is a anion exchange membrane. Now you change the charge, now this surface become cation exchange membrane. Cation exchange membrane means this blue will, you see here. No, sorry. So you are changing the polarity, but you are not changing the charge of the polymer. That is not happening here. But this, when you change the this charge, see the foulant that is, it is uh, gone from the surface. You are not changing the polymer charge, but you are just removing the foulant by this reversing the electricity. Okay, confused? Okay, let me EDR. Okay, EDR has this doubt, right? EDR is, that is the electro. Let me see that if, okay, everywhere it is showing electrodialysis, but okay, then EDR I will tell you. EDR is like you are reversing the flow. Okay, I will tell EDR next class. I couldn't find the videos, but every, okay. This mechanism is clear, how the ion exchange membrane exchange the ions. It is clear, right? Yes, okay. Yes. So I will give the EDR thing next class. So here in the previous class, one more doubt was there. How this organic and metal ions from the wastewater can be best removed by. Which was the answer? Remember? Remember? This carbon adsorption was the most, mostly used carbon adsorption. So there was question how the metal ions can be adsorbed, but here this is possible. See, activated carbon has a higher surface area, and then it is highly porous, and it will amplify sites for the metal ions to adhere. So the answer is carbon adsorption only. It can remove organic as well as metal ions. The previous class this was the doubt. Metal ions can be possible by this adsorption. It is possible, it is way more possible. So here carbon adsorption can, it will adsorb organics as well as metal ions. You can see how the metal ions can be interact with the activated carbon adsorption, by how it can be adsorbed. So different chemical interactions also given, you can read. So this answer is carbon adsorption only. So I have this problem. I think problem I will take next class. Any doubt is there in this class? EDR I will take next class. It's just reversal of this EDR only. I will explain with something. So this mechanisms are clear, right? This ion exchange things. I hope it is clear. Yes. Any doubt? No doubt about this class. Okay. Huh? SBR. Okay, okay. SBR and SBBR. Okay, okay. 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 SBR and hmm, bio. Yes. 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 I will. Yeah. Yes. Okay. Okay. Yeah. I next class I will clear that. Yes. This one and EDR. Yes. Okay. Any more? No. Okay. Thank you. So we'll stop the class today now. Okay. Thank you.